Hello, today we'll study how to derive the Simpson's one-third rule using Lagrange Interpolating Polynomials. Unlike the rectangle method and the trapezoid method, we use a line segment, a straight line segment, to interpolate 2 points of an interval. That's the trapezoid method. And the rectangle method is like this. We use the left end point, or we use right end point. So we just use line segments there with the rectangle methods and the trapezoid method. Now we try to use a curve to approximate or a function, a simple function to approximate this f of x, and then when we evaluate such a definite integral, we use this curve, this function, a new function, a simpler function, to approximate f of x. So we use its integral to approximate that one. Okay, so for a curve, naturally, as you can tell, a polynomial, yes, that's a typical choice. And for a polynomial, and the rectangle method, the trapezoid method, use a line segment that's linear. Now, then the next choices should be quadratic function, cubic function. Simpson's one-third rule uses a quadratic function to approximate f of x, and Simpson's 3/8 rule uses a cubic function, to approximate f of x over a small interval. Now we just focus on this Simpson's one-third rule, and we use a quadratic function to approximate a curve over an interval. Will that work? You only have 2 endpoints. 2 points can only be used to determine a line, right? We know 2 points determine uniquely a line in the space. So to determine such a quadratic function, we need 3 points to determine the coefficients ABC. So therefore, our choice is this. We try to use 2 consecutive subintervals. We divide given that it's from A to B, right? We divide it evenly into, say, n subintervals. And then that n, it turns out it should be an even number. Why? Because we will use 2 consecutive subintervals, and they will contain 3 points. X, say like this, x1, x2, x3. You have x1, y1, x2, y2, x3, y3. We use 3 points to determine, yes, ABC. So that's the idea of Simpson's one-third rule. We use 2 consecutive subintervals to set up a quadratic function. And so we use this. We will find the value. Eventually, we find the value here, the value this one, 2, this 2, this 2, this 2, this 2, and then find their sum. Their sum will be the final answer. Okay, so we'll see. We use Lagrange Interpolating Polynomial. Now, to make our lives a little bit easier, we just assume these are the 2 consecutive subintervals. Okay, the nodes are denoted by x sub 1, sub 2, x sub 3. Okay, they are relative, and there could be later for the next two consecutive will be x1, x2, x3 will be x3, x4, x5. Then the next group will be x5, x6, x7, right? And now when we move on to the next group, that's x sub 1, x sub 2, x sub 3. To the next, x sub 1, sub 2, sub 3. Yes, so they are relative. Okay, they don't this x sub 1, 2, 3, they do not mean they are the first three nodes. Okay, so we try to set up the equation of such a quadratic equation. Okay, the curve. We set up the quadratic equation by using the 3 points. So, as you can tell, how to set up the Lagrange one? It's p of x will be it's y1, that's f of x1 plus y2 plus y3, right? And now x minus x2, x minus x1, x3, sorry. This is x minus each x value except itself, x minus x1, x minus x3. This is x minus x1, x minus x2. Now denominator, we can set up easily. That's x1 minus x2, x1 minus x3, and x2 minus x1, x2 minus x sub 3, x sub 3, 1, 2. Okay, that's it. So we can set up this. Okay, Lagrange interpolating function. So no any calculations needed. Okay, that's good. So there is a trick here. Okay. We have x sub 1, x sub 2, x sub 3. We will try to express each. So especially, I mean, just x sub 2, x sub 3 in terms of x1. Okay, we'll rewrite to this. We will not let x2, x3 appear in the final function. Okay, so therefore you replace x sub 2, 2, 3, this, all by this, and into this function, and we simplify it, we get this. Do not expand. Do not expand this term and then combine like terms. No, do not. We will keep this. We'll try to keep things like x minus x1 to somehow. That's me. Okay, so, and we also know that x sub 1 minus x sub 2, that's negative h. X sub 1 minus x sub 3 is negative 2h. That's why you see their product is 2h squared, right? So, and it's not painful. It takes time, and we need patience. You can arrive at this step. And now combine like terms, and treat this x minus x1 squared as one term, and that's another term. Okay, so now we integrate this function. We integrate this from x1 to x sub 3, right? Yes, just do it. And remember, we don't need to do which one. If you have x1, x3, you have some function like ax minus, or anything like this, simply x minus x1 squared dx. We don't have to expand this one, right? We simply know that's just 1/3 x minus x1 cubic. X changes from x1 to x3. You see, when you evaluate this function at the lower limit, it's so nice. It's just 0. Okay, so that's why the very trick is this, to express x2, x3 in terms of x1. And do not expand in the process. Okay, this trick works so nicely, not just in this video, this talk, and when you derive all the formulas, it could also be applied. Okay, now we evaluate this polynomial, and you have this guy. You have this. It's this one now, and simplify it. Do some cancellation and simplify it, and you get this. Yes. So for 2 over 2 consecutive subintervals, we get such a formula eventually. That's nice. Okay. Okay, that's this. Next, we want to, that's the formula we just derived. Now we want to get the composite formula for this f of x dx. As said, we will do which one? We'll do this. We'll approximate. We'll find the value over this, the first 2 consecutive subintervals, using the corresponding quadratic function. You get a value there, and then now next, over the next, yes, 2 consecutive subintervals, you use its corresponding quadratic function, the Lagrange interpolating function. Okay, you get another value, and then now next. Okay, so we find their sum. That formula is the composite formula. Can we get that? Yes, we can. Okay, now it's this. The first part you apply to this formula, we have it's 1/3 h. It's y1 plus 4y2 plus y3. The first in 2 consecutive subintervals. Now the second one is 1/3. Remember, y1 this time is y3, and this x4 is x2, so that's 4y4 plus y5. Yes, and then move on to the next, and you'll see it's 1/3 h. That's y5, 4y6 plus y7, and so on. Okay, so what can we do? Okay, now you can tell with these, we combine like terms. First, you can factor out 1/3 h. Okay, it's 1/3 h out. And how many y1? Only one y1. How many y2? You have 4y2. How many y3? We have 1, 2. You have 2 y3. And y4? Okay, plus 4y4. How about y5? You have 2y5. And y6, 4y6. And plus how many y7? You have 2y7, and so on. Yes. So And the last term, until we will arrive at which one? The last one, you will have which thing? You have, for the last one, you have this 4y to the last one, given that we have a totally n subintervals. It's even. It's even. Okay, it's even. Okay, it's even. And that one, it's n, capital N minus 1. The last one, we don't have the next one. That's just 1. It's just which one? It's y sub m. Yes, so that's why we have such a formula. Okay. Yes, this is y1, this is y sub m. And for those terms, you see, it's you have 2, 4, 6, 2, 4, y2, y4, y6, and minus 1. Okay. Oh, it's fine. Okay. And here, m, and I just use m minus 1. And I name it, this is xm, that's x0. Okay, it's fine. It's fine. So, and so if n subintervals, if you name the first one x1, that one will be xm plus 1. Yes. Therefore, this is m. That will be m plus 1. So it depends. It depends how we name, label, give the index value to which one? To the fourth one. Okay, so, and 7, those multiplied by 2 until which one? Yes, this, minus 1. And finally have y, the last one is y sub m, m plus 1. Okay, so that's the formula. So we have started how to derive Lagrange Interpolating Polynomial. Oh no, the Simpson's 1/3 formula using Lagrange Interpolating Polynomial. Okay. This usually we use. This is a very nice formula. And next I show you, not in detail, the accuracy of this formula is the truncation error is that, oh my, it's very nice. With the trapezoid method, the midpoint method, it's big O of h squared. With the rectangle method, using the left endpoint, right endpoint is big O of h. You see, this is much better. And Simpson's 1/3 rule, and Simpson's how about 3/8 rule? It's also this, so no big difference. Okay. And while we have 2, oh yes, if they have the same truncation error, it depends. And if the points are given, we have no choice. If they are set up, we only have even number of their points, we will use Simpson's 1/3. I mean, if we have an even number of subintervals, we use Simpson's 1/3 rule. If the number of subintervals is divisible by 3, we'll use Simpson's 3/8 method. Otherwise, if we have the freedom to choose no other constraints, each one is fine. Okay, and the code is so easy. We don't need to code at all. So it just say, hey, this is the function, AB's value, and how many intervals we will have. Oh, we need to have an even number of subintervals. Okay, and then use that, we determine the step size, and we generate the data, and which is calculated. Find the sum here. That's the typical code. You find the sum for this. You see, I name it sum 246, and you find the sum of this term. You say, hey, that's the sum 357. Okay, name it, and later that's direct translation. Okay, And with MATLAB LUO approximately, you can use even shorter code like this. That's LUO approximately. MATLAB's code is even shorter. Okay, and because it can handle slice of a vector or a matrix in a easier way, simpler way. With LUO, it's hard because the language itself doesn't allow me to do more. So I had to use functions like copy, and so that's the only thing LUO approximately cannot compete with MATLAB. Otherwise, and but anyway, what MATLAB could do here with vectors matrices, LUO approximately could do. And only when we need to address pieces, slices of a vector matrix, LUO approximately will use a way like this. That's not as canned as in MATLAB. Okay. Okay, the truncation error of Simpson's one-third rule, and they forget about this. We'll use which one? And again here we try to examine the truncation error with two consecutive subintervals. Okay, and now we have a formula for this one, right? Yes. H will be this. And so we have the very formula here. We have the formula here. Okay, change x1, x3 to AB. It's because I don't want to type x sub 1, x sub 2. It's just use AB. It's easier to type. Okay. So we will find f of x. This guy we want. That's exact value. We use its Taylor series expansion. Taylor series to replace it. So f of x is Taylor series expansion at a the low limit. Okay, it's this. We just use the first 5 terms, and this y2 is that. Okay, we also use its Taylor series expansion at a. This one at a will get this. And we will have this f of b, right? We'll use its Taylor series expansion at a. Okay, and then evaluate at b. Okay, now we put all these Taylor series expansions into this expression. And after some manipulation, a lot of work, I did it just once a few years ago. Normally I would never redo it again. It's time consuming and energy. It's patience consuming. Okay, so you arrive at this. That's which one? That's the truncation error over 2 consecutive subintervals. Now, how about totally? You add all these errors together. Okay, the first pair of 2 consecutive intervals, the second one, the third one. Okay, you just find their sum, and therefore after we use this f bar to denote the average value. Okay, of f bar. That's f the fourth order derivative of f. If that the bar, that means the average value of which one? The fourth order derivatives at yes, which one? At those points. And remember, h is given by this, so you replace into this and this you get that part. So that's why it's big O of h to the fourth. Okay, for the composite formula. Oh, okay, that's it. So, and the topic could be yes, teachers, if we spend more time on the first one slide, second slide, how to show step by step using Lagrange interpolating polynomial. Okay, and that's why with my residential classes, I give them handouts. Okay, I not do all this in on the whiteboard. Okay, it's quite dangerous. Okay, and many textbooks ignore this. They just so many textbooks they simply give you the formula. And I do wish you know how we could get the formula. Okay. Thank you for watching.